Hello everyone, Hardware City Online again. It's better. You see, I have a new shirt. Well, the red one was more comfortable, but I thought it was time for a change. And I think this one is also very nice. Okay, my new sequel of Hardware City now is going to deal with very simple single-bit UART interface. So my goal was, when I want to implement some kind of, let's say, remote control and just want to switch on or switch off a relay or a lamp or LED, something like that. So I just want to transmit a command to a distant station via cable or via Bluetooth, and all I want to do is to light up a LED or switch a relay on or off. And I don't want to use a microcontroller for this. All those setting up stuff with the microcontroller, the configuration and setting up a project and doing the programming stuff. Also for people who are not so skillful in programming microcontrollers. I hope there are still some of these guys out there. So I thought, I had some thought it would be possible to make a more simple approach, to use only a very limited amount of hardware to achieve this goal. And I think I have a very tricky and interesting little solution I want to show you now. And we start. Okay, this is it. You see, we only have three main components, three digital circuits. One circuit is just an inverter, a hex inverter. Second circuit is a normal D-latch flip-flop, dual latch, and third one is a standard and my most beloved integrated circuit, the NE555 monolithic timer circuit. And some smaller parts, some resistors and capacitors and a diode. Okay, and this is the most simple approach I could find for myself to get an LED on and off with the UART interface. The UART interface, as you know, is a serial interface that has an idle state of high. That means normally on the receiver line, and we only need this receiver line here, we don't do any transmissions, we just want to receive a signal and switch on and off an LED. The idle state is high, and the transmission starts with a 0 bit. That means the signal is going down to 0, and so the receiver side should detect this as a start signal of the transmission, and then we have the bits 0, 1, 2, 3, 4, 5, 6, 7 coming one by the other sequentially, and at the end we have 1 or 2 stop bits. That means that the signal is high again. Okay. What happens here is that this receiver signal is fed into this logic here, and first we have an inverter. That means that the idle state here is transformed from high to low, and that means that the falling edge here on the start of the transmission is converted into rising edge here, and the rising edge is setting this flip-flop here, this D flip-flop. The data input is set to high, so that means that the rising edge here is setting this flip-flop. When the flip-flop is set, the inverted output here is going to 0, and the 0 output here triggers our NE555 timer. When the timer is triggered, its output, this is pin number 3, is getting high. With the output going high, the reset input of this D-latch is set to 1 almost immediately, and it's held to 1 even when the NE555 switches back to to 0 volts when the timing impulse is over. This configuration here made out of this resistor and this capacitor, they are holding the high level for a while, for some milliseconds, and keeping this delatch in the reset state. So that means that additional impulses coming here on the line, that following the 0 bit here, and the start bit, cannot re-trigger this flip-flop anymore. So this ensures that the only triggering is done by the start bit and not by the following bits. Okay. The pulse width specified by those two resistors here and the capacitor is done in a way that the NE555 switches back to normal mode. That means the output going low again when the special bit in the transmission, in the UART transmission, arise that you want to detect. So that means the switching back of the NE555 is fed here through the inverter and to a second D flip-flop, which is part of the same circuit. There are two flip-flops on the circuit. The NE555 generates a rising edge because the inverter is here, and this is used as a clock signal for this second flip-flop, for this latch. And you can see that the data input here is directly connected to the receiver line. So that means that this flip-flop gets the latch signal right at the moment where the respective bit arrives that you want to switch on or off. And that's all. The output here is routed through the resistor to a diode, to an LED, so that we can see if it's on or off. So that means the bit you want to detect with this circuit here is just specified by the pulse length of the NE555. So by varying this pulse length, by varying this resistors here, you can detect any bit you want, starting from bit 0 up to bit number 7. And here in my drawing I also showed some configurations when you want to choose a special bit. The basic configuration now here is specified for bit number 0, but you can also easily change these resistors by keeping the capacitor the same for all the other bits. So that's really very easy. And now I'm going to show you my breadboard. This here is the NE555. Here we have the hex inverter 4069, and here we have the 4013, the two D latches. This is a power supply, 5 volts, and here you can see the diode. This module here is a standard Bluetooth module that is configured for a baud rate of 2400 bauds, because my whole circuit is laid out for 2400 bauds, which should be really enough to switch on and switch off single bits. Now we set this under voltage. You can see now the module here is blinking because it's not yet connected. The LED is high. This is still an issue with the reset. I have to make up my mind about this, but this is not a very big problem. And here I have my tablet PC, and I've written a small program in a language called Taurus Basic, and Taurus Basic also provides library functions for using the Bluetooth interface as a serial COM port. This is what I'm going to show you now. Okay, let's start the program. This program is very simple. It gives me a list of all the Bluetooth devices that are found in the environment. I can check this one, which I named M sensor, and now it's trying to connect it. Okay, got it. You see the blinking now is off, and now I can enter a byte value. It's going to be transmitted. I enter 0, and now see what happens with the LED. It's going off. Now I enter 1, and it's going on. 0, it's going off. And to show you that really only the first bit now is sampled, I'm going to enter a 2, which means the second bit is set, and it stays off. I enter 4, which means the third bit is set, off. I enter 8, third bit is set, off. Now I enter 16, off. 32, off. 64, oh, okay. 64, oh, okay. There seems to be a remaining problem with the pulse width, but I think I can fix this by adjusting the pulse width. Or maybe it's the configuration with the resistor and the capacitor here, because the time constant that is achieved by this configuration defines when the hardware is able to be re-triggered. And maybe this is too early now, so maybe I have to make this capacitor a little greater. But you can see principally it works. So that's an easy way for you to do some kind of remote controlling domestic application or whatever you want by using only a handful of integrated circuits and some resistors and capacitors and a diode. Okay, thanks for watching.